This presentation is about an application of energy informatics to the greening of greenhouses. The goal is to reduce the energy required to grow crops. Food security is a macro problem for the world because over the next 30 years, the population will grow by 34% and urbanisation will grow by 20%. An urban population tends to be richer and eat more. As a result, food production must grow by 70%. As this slide illustrates, some very fanciful designs and ideas have been put forward for growing food in urban areas. However, it's much better to grow food in low-cost areas and take full advantage of natural sunlight. Photons generated by the sun are free, so it's typical for a greenhouse to have a large open area to enable as much light as possible to enter the growing space. The ideal situation, as shown in the lower right photo, is to grow plants outside. But sometimes, if you're trying to meet particular market demands, you need to grow them in a controlled environment so you can provide heating and cooling as required. The slide on the upper right shows the heating system for the greenhouse shown on the left side. This is often required in winter months in order to ensure that the plants get enough heat as well as light to meet demands for delivery on specific dates. This video talks about an entrepreneurial initiative to grow local food in a controlled environment. In 2019, the University of Georgia, plus some partners, received a large grant from the US Department of Agriculture to look at the use of LED lighting to improve the profitability of greenhouse crop production. We call the project LAMP, Lighting Approaches to Maximise Profit. The project examines various ways in which LED lighting can be used to increase crop quality and growth and minimise the cost of energy used to grow greenhouse crops. On a previous slide, I talked about the larger problem of food insecurity. Now we'll move down to the micro problem, where we'll consider the growth of each particular crop. Each plant species has an optimal light intensity that will maximize photosynthesis and plant growth. However, if it receives insufficient light, growth and crop quality can decline, which for a greenhouse grower means that they may not be able to meet the contract requirement to deliver so many pounds of lettuce, for example, to a large food retailer. When there is excessive light, photosynthesis and growth will not increase. It's a saturation curve, so there's a certain point where more photons don't increase the growth of a plant. When there is insufficient light, greenhouses supplement the natural light with artificial light, typically these days from LED lighting, to achieve growth targets. Artificial lighting requires energy, and this can be as much as 30% of the cost of operating a greenhouse. Plants need photons to grow, and they don't really care whether the photons come directly from the sun or from artificial lighting. A plant needs somewhere between 3 to 30 moles of photons per day for optimum growth. One mole is about 10 to the 23 photons. In order to minimize energy use, we need to know the growth curve for each plant and the number of photons it needs each day to meet growth targets. In this graph, you see the growth curve for lettuce. These curves are established by hooking up sensors to a plant and recording the photons received and the electrons produced within the plant. Electrons are required for growth, and the electron transfer rate is a measure of the growth of the plant. As you can see, this is a saturation curve. At a certain point, photons received do not increase the electron transfer rate or the growth of the plant. Ideally, you want to operate in the bottom left corner of the curve where you get more electrons for the number of photons received. In this graph, ETR stands for electron transfer rate, and you can just think of this simply as number of electrons produced, and ppf stands for photosynthetic photon flux. Just think of this as the number of photons received. The University of Georgia Climatology Lab was able to supply us with radiation data for Athens, measured over 5 years at 2-minute intervals. For optimum growth, a lettuce needs 3 moles of electrons per day. As this graph shows, there are some days on which there is insufficient natural light received in Athens for a lettuce to meet its target of 3 moles per day. On these days, supplementary lighting is required to add the additional photons to reach the 3 moles per day. Of course, you also see many days on which the 3 moles is exceeded, but the plant can't take advantage of these additional photons once it's essentially reached its 3 mole target for the day. You can't store the photons for another day. The curve in the previous slide showing the growth of a lettuce plant can be described by the first function for electron transfer rate. We can rearrange this equation to get the second one on this slide, which shows the photons required to meet a target electron transfer rate. For precision growth, we need to manage the number of photons that a plant receives during the day. We start with identifying D, the electron transfer rate, in order to maximize growth. We can then compute the minimum number of electrons that need to be transferred or generated by photosynthesis. Knowing the required number of electrons, we can then compute the required number of photons, the final formula on this page. The innovation developed at the University of Georgia is to dynamically measure the number of photons received by plants in a greenhouse and adjust LED lighting so that the plant receives enough photons to meet growth targets. In other words, if you're above the target, the lights are off. If you're below the target, the lights are raised to a level to meet the threshold number of photons required to generate electron transfer rates needed for the growth of the plant. An important limitation of the innovation is it only measures the light received at a particular point in time. it has no ability to forecast the light received throughout the day. On a day when you have a cloudy morning and a sunny afternoon, the system is likely to generate more photons than are required to meet the plant growth target. The system would work much better if there was a forecast of the solar radiation to be received across the day. Then you could turn on the lights just to generate sufficient photons throughout the day to meet the target of, say, 3 moles per day required by a lettuce. The goal is to deliver exactly the right number of photons and, as a result, minimize the energy required to operate artificial lighting. In order to do this, you need a digital data stream forecasting the number of photons to be received, say, for example, each 10 minutes throughout the day. And secondly, you need a database for each type of plant so you can identify the number of moles it requires and the growth curve that it follows. We recognized that managing the lighting in a greenhouse is an application of the Energy Informatics framework that I introduced earlier. We need a sensor network that measures the current level of solar radiation being received in the greenhouse, so we know whether or not to supply additional photons to a plant. There are 2 flow networks to manage: the electricity flow network for providing energy to drive the LED lamps, and also we need to manage the number of photons being generated in order to supplement the growth of the plant. The third element is the LED lighting. This is the sensitized object that we can turn on and off and adjust the number of photons to be received by the plants at any time. There are 4 inputs that the information system needs: an energy price forecast, so that we use energy when it's cheapest; a solar radiation forecast, so we know when the artificial lighting needs to be turned on. We need a plant database, so we know the characteristics of each plant in terms of the number of photons that it must receive and the growth curve that it follows. And finally, we need a production schedule for the greenhouse so that we can plan for growth throughout the year based upon solar radiation forecasts for the year. We built a simulation model to test our ideas and to estimate the energy savings that could be provided by the application of precisely controlled lighting for a greenhouse. The simulation adjusts LED lighting to maintain the threshold level of photons required by a plant. The goal is to add additional lighting as required to meet the number of required photons for the day based upon a solar radiation forecast for the entire day. We also consider electricity prices. So our goal is to generate photons when they are cheapest and meet the target for the day. We first simulated the adaptive lighting. Remember, this is the dumb lighting that comes on and off based upon the number of photons currently being received. You will see from this graph that there are many days when it costs very little to operate the lights, and a few number of days, the cloudy days, when the lights are on for a considerable time. The total cost of operating adaptive lighting over a year is $39 per day when there are 1,000 lights in the greenhouse. Our second simulation examines the situation where we look at the solar radiation forecast for a day and decide whether the lights should be turned on for the entire day or turned off for the entire day. As you can see, on many days the lights are not turned on, which means zero cost, and there are a few days when they have to be turned on. The problem with this model is on some days the lights might be turned on when only a few photons are required, but remain on for the rest of the day. So it is a better solution than the adaptive lighting, but still not the best solution. Notice that it now costs $16 per day for 1,000 lights in the greenhouse. Our final model is very precise. It measures the natural light received at 2-minute intervals and makes a decision as to whether to turn the lights on or off for the next 2 minutes, and repeats this process throughout the day, at the same time minimizing the cost of electricity throughout the day. The outcome is that now the cost of running 1,000 lights per day is $5. This is a considerable saving from using adaptive lighting. Our simulation models clearly demonstrated that the application of energy informatics principles could be usefully applied to reduce the cost of operating a greenhouse. We built our model based upon known data for lettuce. To apply it to other plants, we need to know the right value of D, the threshold number of photons to be received each day, and the parameters for each crop plant. That is, we need to know the shape of the growth curve. We also need to understand how sensitive the growth outcome is to decision frequency. In the final simulation model that I showed you, we made decisions every 2 minutes. Is this frequent enough? Or could we get away with making decisions every 30 minutes or every 60 minutes? Finally, we need to know the relationship between lead usage and electricity and demand and supply by location. The figures for the simulation are based upon electricity at 12 cents per kilowatt hour at a fixed price throughout the day. However, other locations may have dynamic pricing, and we would have to adjust the simulation model to handle this situation. Finally, the most important point is what is the impact of a precisely controlled LED lighting system on grower profitability. Our initial estimates indicate that we should be able to produce a saving of about 60% on lighting, and as this is 30% of the cost of operating a greenhouse, the return on investment is generally supportive of an investment in precise lighting for greenhouse for plant growth management. The simulation models we built in R, based on application of energy informatics principles, were a component in the successful grant proposal. We're now in the process of building a decision support system for greenhouse growers, and other research is looking at how varying the frequency of LED lighting impacts plant growth and plant quality. The results of our work will be used to improve the profitability of greenhouses throughout the United States.